In Part 1 of Lecture 6, we will discuss concurrent processes, race conditions, and mutual exclusion. Many operating systems do a great deal of their work in a process-oriented fashion, with several different tasks going on more or less at the same time that work in a cooperative fashion. It becomes obvious pretty early that they need some way of coordinating what it is that they are doing. Imagine a situation where you have a checkbook manager running on a computer where there are two separate processes, one handling deposits and other credits, the other handling checks and other debits. They both need access to the balance. This may not seem like the best way to manage your money, but it isn't really such a stretch if you share your checking account with your spouse or significant other, or if you are one of several people checking store inventory before ordering something. P1 will contain the statement balance equals balance plus deposit. P2 will contain the statement balance equals balance minus check. In both cases, they can change the balance. This will happen after they access the value, but not necessarily before the other process accesses it. This means that the process may obtain a value of the balance that is no longer accurate, and that after changing that value, it will fail to reflect one of the two transactions. This is more apparent if you look at the machine language version of the program. It makes it more obvious that changing the balance to reflect a check or deposit involves several steps, and that these steps may occur at more or less the same time as the steps that the other process takes to do its job. This results in a race condition, where the result is determined in an arbitrary fashion by whatever process wins the figurative foot race. A race condition, as the name implies, is a situation where the result depends on who wins the race, and it's not in a methodical fashion that guarantees that everyone's needs are accounted for. In real life, a race may get a younger, more agile person a seat on the subway, instead of the little old lady who needs it more. But in that case, at least the result is predictable. In operating systems, we can't predict which process is the teenager and which one is the little old lady, and that is easily part of the problem. One mechanism that helps us avoid race conditions is protecting what we call critical sections. A critical section is a section of code that must be performed without any interruptions whatsoever. Critical sections are frequently referred to as being atomic, that is, they cannot be divided. Just as atoms could be divided, so can critical sections, although in both cases we know that it is a very bad idea. In implementing critical sections, we recognize that there are four criteria upon which they depend. Only one process can be executing a critical section at a time. If there were more than one, they could interfere with each other in an inappropriate way. We make no assumptions about the speed of the processor or how many there are. The same principles should apply in any case. To avoid a race condition, we will not allow any process outside a critical section from blocking another from entering it. This would possibly lead to a race condition, and no process should wait forever to enter a critical section. This means that we will not allow starvation. Let's take another look at how our concurrent checkbook processes would work once we start guarding our critical sections. They still have balance as a shared variable, but now there is another shared variable, the Boolean variable lock. Each process starts off by checking to see if the lock has been set. If that's the case, it busy waits until the lock is cleared. Once that happens, each process stops busy waiting and sets the lock, adjusts the balances, and then clears the lock. By doing it this way, it cannot be interrupted while it is changing the shared variable. Mutual exclusion means that one and only one of these processes can access a critical section at a given time. They mutually exclude each other. We already know that mutual exclusion is a requirement of any critical section. Not only can't we have these sections interrupted, only one process can run this code at a time, even if there are two processors working at once, which would eliminate the problem of interruption. However, this leaves an important question. How do we implement this? Decker looked at a problem where two processes share a critical section of code to which they need access. In a first attempt to achieve mutual exclusion, he simply added a shared variable called turn. When one variable wants the critical section, it first checks to see if it's its turn. If not, it busy waits until it is. Then we can run the critical section, and then we can turn it over to the other process. This is inherently flawed because it requires strict alternation. If process 1 needs it several thousand more times, while process 2 needs to run that critical section only a dozen times, process 1 will be forced to slow down to match process 2. Also, if either process fails inside or outside the critical section, the other is blocked from re-entering the critical section. These are examples of coroutines, two procedures that pass control back and forth between themselves. Here we attempt to fix it by having each process use a Boolean flag to tell the other whether it is using the critical section. If one process is busy waiting while the other process's flag is set, we wait for the other flag to be cleared. When that happens, that first process sets its own flag and enters the critical section. After completing the critical section, it clears its own flag. If one process fails outside the critical section, the other process can still enter the critical section. However, if a process fails while inside the critical section is permanently blocked. The bigger problem is that this doesn't guarantee mutual exclusion. If process 0 leaves the while loop and can't set its flag before process 1 starts the while loop, they both will have the opportunity to enter the critical section at the same time. The exact sequence is process 0 waits in the while loop and finds flag 1 to be false. Process 1 enters the while loop and finds flag 0 to be false. Process 0 sets flag 0 to true and enters the critical section. Process 1 sets flag 0 to true and enters the critical section. This solution cannot be correct. Let's try changing the order of the first two statements in each process. This will eliminate the potential problem of each process having a window of opportunity as the other process is preparing to signal its entry into the critical section. But now it's a different problem. If process 0 sets its flag, and then process 1 does the same thing before process 0 is past the while loop, they both will busy wait forever, each waiting for the other to finish a critical section that they have barred the other from entering. The exact sequence of statements is process 0 sets its flag to true. Process 1 sets its flag to true. Process 0 finds flag 1 to be true and enters the while loop. Process 1 finds flag 0 to be true and enters the while loop. Neither of them will finish the while loop. This kind of standoff is called deadlock. We will be discussing it in detail quite soon. This attempt gets around the problem of a potential deadlock by having the process release its hold on the critical section if it has to wait. While this is better, there is a scenario where each process blocks each other. The sequence is: process 0 sets its flag to true. Process 1 sets its flag to true. Process 0 checks flag 1. Process 1 checks flag 0. Process 0 sets its flag to false. Process 1 sets its flag to false. And then it starts all over. This process is too dynamic to be deadlock. It is usually called live lock in the event that the speed of either process relative to the other changes. The live lock will be broken, but it may take quite a while for that to happen.